good morning students. Welcome to science session for class 9. And today we are going to see an interesting chemistry lesson, that is unit 13, chemical bonding. And here in this session we are going to see what is chemical bond, octet rule, and about the Lewis dot structure. And also we are going to learn about different types of bond, that is ionic bond, covalent bond, coordinate bond, and what is redox. A very good morning students, welcome to science session for class 9, and today we are going to see an interesting chemistry lesson, that is unit 13, chemical bonding. And here in this session we are going to see what is chemical bond, octet rule, and about the Lewis dot structure. And also we are going to learn about different types of bond, that is ionic bond, covalent bond, coordinate bond, and what is redox reaction, oxidation and the reduction reaction, and oxidation reaction that takes place in our daily life. And we are going to do numerical problems based on the oxidation number of different elements. Let's go into the session, children. Now children, we know that the atoms are the building blocks of matter, isn't it? But except the noble gases, no atoms will exist independently. So what happens? They exist in groups, isn't it? So a group of atoms that exist together as one species is called as molecules. So when they are grouped together, there is a force of attraction that holds the atoms together, isn't it? So that is called as bond. So here we are going to study about the chemical bond. So a chemical bond may be defined as the force of attraction between the atoms that binds them together as a single unit, either as a molecule or as a compound. So there is a force of attraction between the atoms that are bind together, that are grouped together, and we call it as a molecule. Now we'll go to Causal-Lewis approach. Now in that we'll be learning about the octet rule, right? Now what do you mean by octet rule? Atoms of various elements combine together to form the chemical compound, isn't it? Now this can be done in various ways. Now why do atoms combine? How do they combine? So these are explained by the Causal-Lewis approach. Now in that we are going to learn about the octet rule, which is also called as electronic theory of valency. Now why do atoms combine? Atoms of all elements combine because they have incomplete valence shell. So what do? They tend to attain the stable electronic configuration. Now for that we need to understand what is stable electronic configuration, isn't it? So a stable electronic configuration is one that the outermost orbit contains 8 electrons. So if there are 8 electrons in the outermost shell or the valence shell, then the configuration of the atom is called as the stable electronic configuration. So to attain the stable electronic configuration, what happens? The atoms may transfer electrons or share their electrons. So that is what we are going to learn in types of chemical bond. Now if the atoms has 8 electrons in the valence shell, then it is said to have the octet rule, or it is called as the rule of 8, means 8 electrons in the outermost shell. Now we can see the electronic configuration of the noble gases. Now we said that the except noble gases, no atoms exist independently. Why the noble gases exist independently? Because they have 8 electrons in their outermost shell. They have stable electronic configuration. Now we'll see the noble gases, inert gases, or the rare gases they are called as, isn't it? Now helium atomic number is 2 and the electronic configuration is 2. Now if you see neon, the atomic number is 10 and the electronic configuration is 2, 8. We know how to fill the orbitals in K, L and M shell, isn't it? We have learnt in the earlier classes, isn't it? Argon, the atomic number is 18 and the electronic configuration is 2, 8, 8. Krypton, the atomic number is 36 and the electronic configuration is 2, 8, 18, 8. So in all the noble gases, if you see, the outermost shell has 8 electrons. So they are said to have stable electronic configuration. So the atoms tend to attain the stable electronic configuration similar to that of the noble gases. Now, to attain the stable electronic configuration, either they can transfer the electrons from one atom to the other, or it can share the valence electrons. Now, if they transfer the valence electrons from one atom to the other, then that type of bond is called as the ionic bond. If sharing of the valence electrons takes place between the atoms, then the bond is said to be covalent bond, right? So now we are going to see the types of the bonds. Now we said that to attain the stable electronic configuration, they transfer the electrons. In the sense, they lose the valence electrons or gain the valence electrons. Now let's see this gaining and losing of the valence electrons with an example. Now let's take the example of sodium. Now sodium atomic number is 11 and mass number is 23. Now how will you represent the geometrical representation of the sodium? Now this is the sodium atom, right? So in the K shell it consists of 2 electrons. Now in the L shell it has 8 electrons, and in the M shell it has 1 electrons, right? So you know the filling of electrons in the orbits, isn't it? So it is 2, 8, 1. So the electronic configuration of the sodium atom is 2, 8, 1. Now this has 1 electron in its outermost shell, isn't it? So to attain the stable electronic configuration, this sodium atom lose an electron so that it has 8 electrons in the outermost shell. So when it loses an electron, now what will happen? It loses an electron, isn't it? So it has 2 electrons in the K shell and 8 electrons in the L shell. Now when it loses an electrons, it becomes a positive ion or cation. So it becomes an ion. So Na plus. Why plus? Because it has lost its electron in the outermost shell. Now what will be the electronic configuration? 2, 8, because it has lost its electron. So the electronic configuration is 2, 8, and this becomes the stable electronic configuration. Now we will see the equation. Sodium atom will become sodium ion after losing an electron. So Na gives Na plus plus E minus. Now let's see the another example. Chlorine. Chlorine atomic number is 17 and the mass number is 35.5. Now let's see the electronic configuration of chlorine. Now it has 2 electrons in the K shell, 8 electrons in the L shell and 7 electrons in the M shell. Now what will be the electronic configuration? 2, 8, 7, right? Now since it has 7 electrons in the outermost shell, it can gain an electron so that it gets 8 electrons in the outermost shell. So gaining an electron takes place in the case of the chlorine. So it gets an electron from another atom. So what will be the electronic configuration? 2, 8, 8, isn't it? Now since it gains an electron, it becomes an anion, Cl minus, right? So it becomes an anion and the electronic configuration becomes 2, 8, 8. So it has 8 electrons in the outermost shell. So it attains the stable electronic configuration. Now what will be the equation? Chlorine gains an electron and becomes chlorine anion. So Cl plus E minus will give you Cl minus. So we said that by gaining an electron or by losing an electron, the atoms becomes an cation or anion and they attain the stable electronic configuration, isn't it? Now which atoms tend to lose an electron and which atoms tend to gain an electron? We'll see that. So we will see the valence shell, isn't it? Valence shell electrons or valence electrons. The electrons in the valence shell is called as valence electrons. Now atoms with 1, 2 and 3 electrons in their valence shell will lose the electrons and attain the stable electronic configuration. Now atoms with 5, 6 and 7 electrons in the valence shell, or if the valence electron is 5, 6 and 7, it gains the electron so that it get 8 electrons in the outermost shell and attain the stable electronic configuration. Next we'll move to Lewis dot structure. Now we said that the atoms combine to form the compounds, isn't it? And when they combine the compounds, the valence electrons involved in bonding, isn't it? So there is a method. It is helpful to have a method which depict the valence electrons in the atom. So the Lewis dot structure helps to depict the electrons in the atoms. Now this Lewis dot structure is also called as electron dot structure, and we use dots to indicate the unpaired electrons and paired electrons in the valence shell. Now the unpaired electrons are denoted by the single dot and the paired electrons are denoted by a pair of dots. Now let's see the examples how the valence electrons are depicted in the elements. Now first element is hydrogen. The atomic number is 1, and what will be the electronic configuration? 1. So how many valence electrons are there? 1, isn't it? Now this is the symbol of hydrogen, isn't it? Hydrogen. The symbol of hydrogen is H, and it has 1 electrons, 1 valence electron. So 1 dot, single dot. So unpaired electrons. Next comes the helium. Atomic number is 2. Electronic configuration is 2. There are 2 valence shell. So He, and you have 2 dots. So this represents the paired electrons, right? Now beryllium, atomic number is 4. Electronic configuration is 2, 2. So there are 2 electrons in the valence shell, and beryllium symbol is Be, and it has 2 single dots. So 2 unpaired electrons. Next is carbon. Atomic number is 6. Electronic configuration is 2, 4. So how many valence electrons are there? 4 valence electrons. So carbon symbol is written in the middle and 4 dots on all the 4 sides. So this represents the valence electrons in the carbon. Next is nitrogen. Atomic number is 7 and the electronic configuration is 2, 5. So there are 5 valence electrons, and here you have 1 paired electrons and 3 unpaired electrons. So this is how it is represented. Next comes the oxygen. Atomic number is 8 and the electronic configuration is 2, 6. So there are 6 electrons in the valence shell, and you have 3 paired electrons in the outermost shell. So this is how the Lewis dot structure, or it is also called as electron dot structure, right? Now this is a very important question, children. So you can copy this 6 elements in your classwork. Next we'll move to the types of chemical bond. Now this chemical bond is divided into strong bond and weak bond. Now see the strong bond, children. It is further divided into 4 types. The first one is ionic bond, covalent bond, coordinate bond and metallic bond. Now if you see the weak bond, it is divided into 2 types, hydrogen bond and van der Waals interaction. So this is how the chemical bonds are classified. Now we are going to see the strong bonds, and for your syllabus you have ionic bond, covalent bond and coordinate bond. So in this lesson we'll be dealing with the ionic bond, covalent bond and coordinate bond. Now let's see the ionic bond first. Now the ionic bond is a chemical bond that is formed between the 2 atoms. That is, it is an electrostatic force of attraction between the positive ion and the negative ion. So here the bond is formed between 2 atoms when 2 or more electrons are transferred from the valence shell of one atom to the valence shell of the other atom, isn't it? Now here it is in force of attraction between the positive and the negative ion, isn't it? So when an atom loses an electrons, it becomes an cations or the positive ions. When an atom gains an electrons or gain electrons from the other atom, it becomes an anion, that is the negative ions. So there is a force of attraction between the positive ion and the negative ion. Since there is a force of attraction, that is electrostatic force of attraction between the positive and the negative ion, this ionic bond is also called as electrostatic bond. Now mostly the ionic bonds or the ionic compounds are formed between the metal and the non-metal. Now if you see the group 1 elements, that is the alkali metals, and group 2 elements, that is alkaline earth metals, mostly forms the ionic bond with the non-metals. So most of the alkali and alkaline earth metals forms the ionic bond when it comes in contact with the non-metals. Now let's see an example of the ionic bond. Now let's take the sodium. Now we are taking a sodium atom and an chlorine atom. Now first we'll see sodium. Now we are familiar with the sodium electronic configuration, isn't it? Now what is the atomic number of sodium? Atomic number of sodium is 11, right? Using the atomic number we are going to find out the electronic configuration, isn't it? So 11 is the atomic number. So what is the electronic configuration? 2, 8, 1. So it has 1 electron in its outermost shell. Now if you see chlorine, the atomic number is 17. So how many electrons are there in the first shell? 2, then 8, then in the outermost shell it has 7 electrons, right? Now here the electronic configuration is 2, 8, 1. So it can lose an electron and become a positive ion. Chlorine, its electronic configuration is 2, 8, 7. So it has 7 electrons in the outermost shell. So it can gain an electron from the sodium atom, and it can have 8 electrons in the outermost shell. So this loses an electron, right, and it is gained by the chlorine. Now here you can see 1, 2, 3, 4, 5, 6, 7, right, and it gains an electron. So I have denoted as in circle, right? So the electrons in the sodium is represented by a circle, isn't it? And the electrons in the chlorine is represented by a circle which is shaded, isn't it? So you can differentiate. This electron is from the sodium atom, right? So when it gains and loses, now what happens? This becomes a positive charge, right? Now what will be the electronic configuration of sodium? It is 2, 8 because it has lost an electron. Now here, since it gains an electron, chlorine attains the electronic configuration 2, 8, 8. So there is a force of attraction, that is electrostatic force of attraction between the positive and the negative ion, and this forms an ionic bond. So an ionic bond is formed between the sodium chloride compound by losing an electron from the sodium, and it is gained by the chlorine, right? And both attains the stable electronic configuration, that is the 8 electrons in the outermost shell. Now let's see one more example of formation of ionic compound. Now here we are going to see the formation of ionic bond between magnesium chloride, that is MgCl2, right? Now here in MgCl2 you have 1 magnesium atom and 2 chlorine atoms. Now here we are going to find the formation of the ionic bond. Now let's see first magnesium. Now magnesium atomic number is 12. The electronic configuration of magnesium is 282. So it has 2 electrons in its outermost shell. And to attain the stable electronic configuration, so it has to lose its 2 electrons from its outermost shell, and it will acquire a stable electronic configuration similar to that of the neon. Now on the other hand, we have chlorine. So there are 2 chlorine atoms. The atomic number of the chlorine is 17, isn't it? So what is the electronic configuration? 287. So it has 7 electrons in its outermost shell. Now it can gain an electron from magnesium to attain the stable electronic configuration. So each chlorine gets 1 electron from the magnesium, and both the magnesium and the chlorine attains the stable electronic configuration. Now you can see here that the magnesium loses its 2 electrons, and by losing 2 electrons it attains the electronic configuration of 2, 8. So on losing 2 electrons it becomes magnesium cation, that is Mg2 plus, because it has lost its 2 electrons. So it becomes magnesium cations. Now you can see the electronic configuration, it is 2, 8 for magnesium cation. Now here chlorine has gained an electron. Each chlorine has gained one electron from the magnesium, isn't it? So now the chlorine anion, since it gains an electron, it becomes an anion, and the electronic configuration becomes from 2,8, 7 to 2,8, 8. So you can see here that it contains one atom that is gained from the magnesium. Electrostatic force of attraction exists between the magnesium and chlorine, and the formation of MgCl2 takes place. That is the formation of the ionic bond in magnesium chloride. So this is about the formation of magnesium chloride. Now let's see the characteristics of ionic compound. First is the physical state. Now these compounds are formed because of the electrostatic force of attraction between the positive and the negative ions, isn't it? So these compounds are mostly crystalline at room temperature. The next one is the electrical conductivity. Now, since they are the crystalline solids, the ions are tightly packed, isn't it? So they cannot move freely. They just vibrate from its own position, isn't it? So they do not conduct electricity in the solid state, but in molten state, their aqueous solutions conduct the electricity. The next one is the melting point. Now melting point, since they have strong electrostatic force of attraction between the positive and the negative ions, it needs very high energy to separate them, right? So it will have high melting point and boiling point. The next one is the solubility. Now these ionic compounds are soluble in polar solvents such as water, and they are insoluble in non-polar solvents such as benzene and carbon tetrachloride. Next is the reactions. Now since it forms an ionic compound, it undergoes only the ionic reactions which are very fast and spontaneous. So next we are moving to the next type of chemical bond, that is covalent bond. Now we said earlier, isn't it, and sharing of electrons lead to covalent bond. So the atom can combine with another by sharing an unpaired electrons in their outermost shell. So a bond formation needs an electron pair, isn't it? So each of the two combining atom contributes one electron to the electron pair that is needed for the bond formation. Now when an atom forms a covalent bond between them, each of the atom that is contributing an electron will attain this stable electronic configuration. Yes or no, children? Yes. Now, since the electron bond is formed because of the sharing of electron, this electron that is shared in between becomes common to both the atoms, and this covalent bond is also called as atomic bond. Now we'll see an example. We'll see the general example. Now here you can see that an atom A consists of an electron which is denoted by X, isn't it? An atom B consists of an electron which is denoted by N square, isn't it? Now when they share an electrons, when they form the covalent bond, sharing of electrons takes place in between the two atoms, isn't it? Here you can see that in between the electrons is shared, isn't it? Now this electron pair is common to both the atoms, isn't it? Now each is contributing, that is each atom is contributing one electron to the electron pair for the bond formation. And what is formed? A covalent bond is formed between the two atoms. So this is how the formation of the covalent bond takes place. Now let's see an example for the formation of the covalent bond. So here we are going to see the formation of hydrogen molecule, isn't it? How is an hydrogen molecule formed? Hydrogen molecule is formed by two hydrogen atoms, right? So while forming the hydrogen molecules, both the hydrogen atoms will contribute one electron, right? Now see here, hydrogen has one electron in its outermost orbit, isn't it? Now here also you have one hydrogen with an electron in its outermost orbit. Now when they form the covalent bond, isn't it, these two electrons are shared in between the hydrogen atom. So this is the shared pair of electrons. So each hydrogen atom is contributing one electron and an covalent bond is formed, right? So sharing of electrons between the two hydrogen atoms takes place. Now here what will happen? How is the bond formed? You have one pair of electrons, isn't it? Now how is the bond formed? Hydrogen single bond and hydrogen. So since there is only one pair of electrons, there is a single bond between the hydrogen atoms and an hydrogen molecule is formed. Next, we'll move to the formation of chlorine molecule. Right now, here children, you can see two chlorine atoms, isn't it? Now, we know that the atomic number of chlorine is 17. Right now, what is the electronic configuration? So, the electronic configuration of chlorine is 2, 8, 7. So, it has 7 electron in its outermost shell. So, it can gain 1 electron, isn't it? Each atom should have 8 electrons in its outermost shell. So each chlorine atom needs 1 electron, isn't it? So they share an electron between them to form an covalent bond. Now here you can see the sharing of electrons takes place, isn't it? Now here you can see that the sharing of electrons takes place in between. That is, each is contributing 1 electron to form the bond. Now count the number of electrons in the outermost orbit, children. This is 1, 2, 3, 4, 5, 6, 7, 8. So 8 electrons for this chlorine atom. Now count the number of electrons in this chlorine atom. Here it is 1, 2, 3, 4, 5, 6, 7, 8. Right? So this has 8 electrons in its outermost orbit. So by sharing an electron, both the atoms attains the stable electronic configuration. And what is formed here? Here chlorine. And since you have one pair of electron is shared, so you have single bond between the chlorine. So Cl2 is nothing but chlorine bond and chlorine, isn't it? So that becomes Cl2, isn't it? So there is a single bond between the chlorine atom and chlorine atom, since a single electron pair is shared between the atoms. Next, we'll move to the third example, that is formation of methane. Now, what is the formula for methane, children? Methane formula is CH4. So, you have 1 carbon and 4 hydrogen. Now, look into the picture. Here you have 1 carbon, isn't it? What is the atomic number of carbon, children? Carbon atomic number is 6, isn't it? So, what is the electronic configuration? Electronic configuration is 2, 4. Now here you can see that it consists of 2 electrons in the K shell and it has 4 electrons in the outermost shell, right? Now look into hydrogen. There are 4 hydrogen atoms, isn't it? And each contains 1 electron in its outermost orbit. Now how is the covalent bond formed between the carbon and hydrogen? Now the carbon needs 4 electrons. Since the electronic configuration is 2, 4, it needs 4 more electrons, isn't it? No, it needs 4 more electrons to attain this stable electronic configuration. Now, similarly, if you see hydrogen, it needs 1 more electron, isn't it? Now, each hydrogen contains 1 electron in its outermost shell. So, it needs 1 more electrons to attain the stable electronic configuration is 2. Because the maximum number of electrons that can occupy in the K shell is 2, isn't it? Now, here I cannot go for finding 8 electrons because it has only one shell, that is the K shell. And the maximum number of the electrons that is occupied in the K shell is 2. So, it needs 1 more electron. Now look into the formation of the covalent bond, children. Now here you can see in between that 2 electrons are shared between the carbon and hydrogen. Now here you can see that the red dot indicates the electrons from the carbon and the green dot is the electrons from the hydrogen. Now in between you can see, isn't it, very clearly it is mentioned that the electrons are shared between the carbon and hydrogen. So each hydrogen is contributing 1 electron to the carbon. So carbon attains the electronic configuration of 2, 8, right, by gaining 4 electrons from the hydrogen. Now similarly, if you see hydrogen, it has 1 electron in its outermost shell and 1 electron is contributed by the carbon atom. So totally it has 2 electrons in its outermost shell. That is, each hydrogen atom has 2 electrons and attains the stable electronic configuration. Since one pair of electron is shared between the carbon and the hydrogen, now how will be the bond? I said single pair of electrons, a single bond, isn't it? It's carbon in the middle and the single bond is formed between the hydrogen. So this is how you represent the methane molecule. So carbon in the middle and carbon has 4 bonds around it, isn't it? So bond in the sense 2 electrons in between the bond. So the bond represents 2 electrons are shared between the atoms. Next, we'll see the formation of oxygen molecule. Right now, what is the atomic number of oxygen? Oxygen atomic number is 8, isn't it? Now, what is the electronic configuration? Electronic configuration is 2, 6. Right? So, how many electrons are there? You can see 2 here, 2 here and 2 here. So, it has 6 electrons in its outermost shell. Now, similarly, this oxygen atom also has 6 electrons in its outermost shell. Now, how many electrons are needed? It needs 2 more electrons, isn't it? So, similarly, it also needs 2 more electrons, right? So, the electron sharing takes place between the oxygen atom so that each attains the electronic configuration, stable electronic configuration, right? Now look into this picture, children. Here the sharing of electrons takes place, right? So it needs 2 more electrons and this atom also needs 2 more electrons. So here 2 shared electron pair is in common, isn't it? Now if you count the outermost electrons, valence electrons for this oxygen atom, it is 2 plus 2 and 4, isn't it? So totally 8. Now you count for this oxygen atom, it is 2 plus 2, 4. 4 here you have 4 electrons, isn't it? So totally 8 electrons. So each attains an stable electronic configuration, that is, each atom has 8 electrons in its outermost shell by sharing 2 shared electron pairs, right? Now since 2 electron pairs are shared between the oxygen atoms, now the bond formed will be oxygen and it has 2 bonds between the oxygen. Now it means that for this bond 2 electrons and for this bond 2 electrons. So look into the picture here. Here you have 4 electrons in between, isn't it? So 2 bonds, right? Oxygen is usually represented as O double bond O. Now we are going to see an example of nitrogen molecule, right? Now the formation of covalent bond in nitrogen molecule. Now here you can see that the atomic number of nitrogen is 7. So what is the electronic configuration? 2, 5. Right? So how many electrons are there in the outermost shell? Here it is 3 and 2. So totally 5. So similarly for this atom you have 3 plus 2, 5. Right? And how many electrons are needed? 3 electrons are needed, isn't it? So it needs 3 more electrons and it also needs 3 more electrons to attain the stable electronic configuration. The shared electron pair is in common between the 2 nitrogen atoms, right? Now here if you count the number of electrons in the outermost shell, here it is 2, isn't it? And here you have 6, right? So totally 8 electrons for this nitrogen atom. Similarly, you can count for this nitrogen atom. Here you have 2 and here you have 6 electrons in between the 2 nitrogen atoms. So totally 8 electrons. Each nitrogen atom has 8 electrons in its outermost shell. So each attains this stable electronic configuration. Now since it shares 3 electrons in between, the bond is N triple bond N. Now you can see 2 electrons for this, 2 electrons for this bond and 2 electrons for this bond. So totally how many electrons are there? 6 electrons, or you can say 3 electron pairs. So usually we represent nitrogen molecule as N triple bond N. Understood, children? Now, children, we have seen the characteristics of an ionic compound, isn't it? So, similarly, we can see the characteristics of the covalent compound. First, we'll see the physical state. Now, depending upon the force of attraction that exists between the covalent bond, whether it is in strong or the weak bond, the covalent bond can exist in gaseous, liquid, or solid form, right? So, for example, if you see diamond, it exists in solid, and if you see water, it is a liquid. And just now we saw the example of oxygen, isn't it? That is a gas. So, depending upon the force of attraction between the atoms, it can be a liquid, solid, or a gas. Now, electrical conductivity. Now, covalent compounds do not conduct electricity because they do not contain charged particle, isn't it? So, they don't conduct electricity. They are the bad conductors of electricity. Now, if you see the melting point, mostly it has low melting point compared to that of the ionic compounds. Now, if you see few examples, like few exceptions are there. For example, diamond, silicon carbide. So, these are the exceptions which has high melting point. Now, solubility, the covalent compounds, since there is a sharing of electrons takes place between them, non-polar solvents like benzene, carbon tetrachloride can be used as a solvent. That is, it is readily soluble in non-polar solvents, and they are insoluble in the polar solvents like waters. So, it is just the opposite that of the ionic compounds. And if you see the reactions, most of the covalent compounds undergo molecular reaction, right? So, the reactions are little slow. And hardness and brittleness, if you see covalent compounds, they are not hard and they are not brittle, and on the other hand they are soft and waxy. So, these are the characteristics of the covalent compounds. Next, we'll move to the next type of chemical bonding. So, that is coordinate covalent bond. In covalent bond, what we shared, the sharing of electrons takes place, and each atom contributes one electron for the bond formation, isn't it? For the bond formation, an electron pair is needed, and each electrons will contribute one electron. Now, here in the coordinate covalent bond, the sharing of electrons takes place, but both the atoms comes from only one combining atom, right? So, this type of bond is called as the coordinate covalent bond or the dative bond. Since one of the atom gives both the electrons, most of the atoms with lone pair of electrons involved in the dative bonding, right? Mostly the lone pair of electrons from an atom is involved in the dative bonding, and the atoms which donates an electron is called as the donor atom, and the other atom which accepts these lone pair of electron is called as the acceptor atom. And the atom which donates, isn't it? So, it is indicated by an arrow mark. That is, this particular atom is donating an electron to the other atom. Now, see an example. Now, look into the screen, children. Here you can see an example where you have an atom A with lone pair of electrons and atom B which is in short of electrons, which needs electrons to have a stable electronic configuration. And atom A consists of the lone pair of electrons. Now, here the sharing of electrons takes place. That is, the covalent bond is formed between A and B. How is the covalent bond formed? The atom A donates a lone pair of electrons to atom B so that B can attain the stable electronic configuration, right? Now, how is the bond represented here? A is donating a pair of electrons to B, isn't it, children? So, is denoted with an arrow mark, isn't it? Now, what are the examples? NH4 plus NH3 bonded with BF3. Now, look into this example, children. Here you have an coordinate covalent bond, right? A bond between ammonia and boron trifluoride, isn't it? Now, here ammonia has one lone pair of electron, isn't it? And the boron in BF3 is electron deficient, isn't it? It needs electrons. It is given by nitrogen in ammonia to boron, which is electron deficient, right? Now here the ammonia becomes the donor molecule because it donates a lone pair of electron, isn't it? And here BF3 becomes an acceptor molecule. Now how will be the bond represented? So this is the bond formation, isn't it? Coordinate covalent bond. Now how is the bond represented? Can you see here? It is represented as NH3 with the arrow mark, isn't it? So this indicates that the lone pair of electron is from nitrogen is donated to boron in BF3. So this is how the coordinate covalent bond is formed. Now what is the characteristics of coordinate covalent bond, children? It is a type of a covalent bond. These compounds may exist as gas, liquid and solid. Like covalent bond, they do not have charges, isn't it? So they are bad conductor of electricity. Next one is the melting point. Now the coordinate covalent bonds have high melting point and boiling point than that of the covalent bond, but it is less than that of the ionic bonds, if you see. Now solubility, they are soluble in the polar solvents like benzene, carbon tetrachloride and toluene, but it is insoluble in the polar solvents like water. And the reaction, if you see, like covalent bond, it also undergoes the molecular reactions, and these molecular reactions are slow, right? Next we'll see the oxidation, reduction and redox reaction. Now, children, when we cut an apple and when we leave it for some time, what will happen? It turns brown on its surface, isn't it? Similarly, the iron gets rusted, isn't it, when it comes in contact with the moist air. Now, why this happens? All this happens because of a reaction which is called as oxidation, right? Now, what do you mean by oxidation? Oxidation is nothing but a chemical reaction which involves the addition of oxygen or removal of hydrogen or the electron. Electron is removed or hydrogen is removed. So this type of reaction is called as oxidation. Now let's see the example. Now here magnesium comes in contact with oxygen and it forms magnesium oxide. Now here oxygen gets added to the element magnesium. Addition of oxygen takes place, isn't it? So this reaction is called as oxidation reaction. Now we also said that the removal of hydrogen is also oxidation, isn't it? So calcium hydride, now when it decomposes, it forms calcium and hydrogen. So hydrogen is removed from the compound calcium hydride. So removal of hydrogen takes place. So it also comes under oxidation reaction. Now see this example, Fe2 plus, here the oxidation state is 2, isn't it? Now it loses an electron and forms Fe3 plus. Now here the oxidation state is 3 plus. So here after losing an electrons, it moves from the oxidation state Fe2 plus to Fe3 plus. Next is the reduction. Now reduction is a chemical reaction in which addition of hydrogen or the removal of oxygen or the gain of the electron takes place. Now let's see the example. Now sodium, when it is treated with hydrogen, now it forms sodium hydride, isn't it? Now hydrogen gets added with the sodium, isn't it? So addition of hydrogen takes place. So this is a reduction reaction. Now here copper oxide, when treated with hydrogen, it forms copper plus water. Now what is removed? Oxygen is removed from CuO, isn't it? So removal of oxygen takes place in case of copper, isn't it? So this is also reduction. Now here if you see the next example, Fe3 plus, here the oxidation state is 3, isn't it? Now on gaining an electron, it comes to oxidation state Fe2 plus, here the oxidation state is 2. So this is reduction. So after gaining an electron, it gets reduced to Fe2 plus. Here the oxidation state is 2 plus. Now this also comes under reduction. It is the redox. Redox in the sense the reduction and oxidation. So reduction and oxidation takes place simultaneously in a reaction, right? In the same reaction. Then that reaction, that type of reaction is called as the redox reaction. RED means reduction, OX means oxidation. So oxidation and reduction takes place in the same reaction. Now we'll see an example. Here PbO, that is lead oxide, on treatment with carbon, it forms lead, that is Pb plus carbon dioxide. Now see this lead oxide. Now lead oxide on removal of oxygen. Removal of oxygen is also called as reduction, isn't it? So oxygen is removed from the lead oxide and it becomes the metallic lead. Now here the reduction takes place in case of the lead oxide, that is reduced to metallic lead. Now see carbon. Now in the reactant side you have carbon, isn't it? So this gets oxidized, that is oxygen gets added to the carbon and it becomes carbon dioxide. Now the conversion of carbon to carbon dioxide is the oxidation process. So the reduction process and the oxidation process takes place in the same reaction. So this comes under redox reaction. Next is the oxidizing agent. Oxidizing agent is a substance which has the ability to oxidize other substance, right? So it can oxidize other substances. So it is called as oxidizing agent. Now mostly these oxidizing agents will be electron acceptors. That is, it accepts the electrons from the other substances or it removes electrons from the other substances. So it has the ability to oxidize the other substance. Now let's see the example. Hydrogen peroxide, H2O2 hydrogen peroxide, MnO4 minus, CrO3, Cr2O7 minus, that is dichromate ion. So all these are the oxidizing agent. The next one is the reducing agent. The substance which has the ability to reduce the other substances are called as the reducing agent, and these are electron donors. They donate electrons to the other substances, right? Now let's see the examples. Sodium borohydrate, right? Lithium aluminium hydrate, platinum, palladium. So these are the reducing agent which reduces the other substances, which has the ability to reduce other substances. Next is the oxidation number. Now what do you mean by oxidation number? It is also called as oxidation state. Okay, so it is nothing but the total number of the electrons that an atom gains or loses in order to form the chemical bond with the other atom. So simply you can say that the number of electron gains or lost during a chemical bond is nothing but the oxidation number. Now let's see the examples. Now if you take potassium, the oxidation number of potassium is +1, bromine -1, hydrogen +1, oxygen -2. So you have to memorize the oxidation number of these elements so that it is helpful when you do the numerical problems. And we also know that the oxidation number is the number of electrons that gains or lost during the chemical reaction. Now the sum of the oxidation number, if you say for an neutral compound, it is always 0, right? Now example is water, right? Now let's see an example how the oxidation number is calculated. Now the first example is water, right? Now here we are going to substitute the oxidation number of hydrogen and oxygen, and we are going to see that the oxidation of the neutral molecule is 0, right? Now the oxidation number of hydrogen is +1. The oxidation number of oxygen is -2. I asked you to memorize the oxidation number of few elements, isn't it? Now we are going to substitute here. Now how many hydrogens are there? 2 hydrogens. So 2 into the oxidation number, that is +1, plus how many oxygen? 1 into the oxidation number of oxygen -2. So this will become 2 and this is -2. So 2 minus 2 is 0. Now let's move to the second example. Now here we are going to find out the oxidation number of sulfur in sulfuric acid. Now formula is H2SO4. Now how many hydrogens are there? 2 hydrogens into the oxidation number of hydrogen is +1, plus how many sulfur? 1 into X, because we are going to find out the oxidation number of sulfur, plus how many oxygens are there? 4. So 4 into oxidation number of oxygen is -2. Now this should be equated to 0. Always remember that this should be equated to 0. Now here this becomes 2 and here it is 1 and here it is -8, right? And when you subtract 2 minus 8, it becomes -6. So x minus 6 is equal to 0, x is equal to 6. So the oxidation number of sulfur in sulfuric acid is +6, right? Now let's move to the third example. Now here we are going to find out the oxidation number of chromium in potassium dichromate. Now oxidation number of the potassium is plus 1 and oxidation number of oxygen is minus 2. This we know it, isn't it? Now here we are going to find out for chromium. Right? Now how many potassium are there? 2 potassium. So 2 into the oxidation number of potassium is plus 1 plus 2 chromiums are there. So 2 into X plus 7 oxygens are there. So 7 into minus 2 is equal to 0. So this should be equal to 0. So here this becomes 2. This is 2x and this becomes minus 14. So 2 minus 14 is minus 12. So 2x minus 12 is equal to 0. 2x is equal to 12 and x is equal to 12 divided by 2. X is equal to plus 6. So the oxidation number of chromium in potassium dichromate is plus 6. Now let's move to the other example, that is oxidation number of iron in iron sulfate, that is FeSO4. Oxidation number of sulfur is plus 6. We have calculated in the previous example, isn't it? So oxidation number of oxygen is minus 2. How many Fe is there? Only 1. So 1 into X will become 1. Now how many sulfur? 1. So 1 into plus 6. How many oxygens are there? 4. So 4 into minus 2. It should be equated to 0. So is equal to 0. Now this becomes X. This becomes plus 6. And this becomes minus 8. So when you subtract 6 minus 8, it becomes minus 2, isn't it? So X minus 2 is equal to 0. X is equal to 2 plus 2. So the oxidation number of Fe in FeSO4 is plus 2. Now children, in page number 158, above the points to remember, you have 4 problems. So these 4 problems are very, very important. Let's see them one by one. Find the oxidation number of Mn, that is manganese, in potassium permanganate, that is KMnO4. So oxidation number of potassium is plus 1. Oxidation number of oxygen is minus 2. So this should be memorized, isn't it? So now here we are going to calculate the oxidation number of manganese in KMnO4. So how many potassium are there? 1. So 1 into plus 1. Oxidation number of manganese has to be found out, isn't it? So let it be X. Plus how many oxygen? 4. So 4 into minus 2 is equal to 0. Now this becomes 1. This is X and this becomes minus 8 is equal to 0. So when you subtract 1 minus 8, it becomes minus 7. So X minus 7 is equal to 0. X is equal to plus 7. So the oxidation number of manganese in KMnO4 is plus 7. Next, we are going to find out the oxidation number of Cr in sodium dichromate. Right? So Na2Cr2O7. So what is the oxidation number of sodium? It is plus 1. Oxidation number of oxygen is minus 2. Now how many sodiums are there? There are 2 sodiums. So 2 into plus 1. And how many chromium? 2. So 2 into X plus how many oxygen? 7. So 7 into minus 2. That should be equated to 0. So this becomes 2. This is 2X and this becomes minus 14. So 2 minus 14 is equal to 0, right? So 2x is equal to minus 12. So when you subtract 2 minus 14, it becomes minus 12, isn't it? So 2x is equal to 12. X is equal to 12 divided by 2. So x is equal to plus 6. So oxidation number of chromium in sodium dichromate is plus 6. Next we'll move to the third one. Find the oxidation number of Cu in CuSO4. So oxidation number of sulfur is plus 6. Oxidation number of oxygen is minus 2. So here copper, you have 1 copper, isn't it? So 1 into X is X plus how many sulfur? 1. So 1 into plus 6 plus oxygen, you have 4 oxygen. So 4 into minus 2 is equal to 0. So this becomes X and this becomes plus 6 and here it is minus 8. So 6 minus 8 is minus 2. So X minus 2 is equal to 0. X is equal to plus 2. So the oxidation number of copper in copper sulfate is plus 2. Next, see the last sum, right? So find the oxidation number of Fe in FeO. Now the oxidation number of oxygen is minus 2. We know it, isn't it? Now here how many Fe? Only 1. So 1 into X is 1. Now oxygen also you have 1, isn't it? So 1 into minus 2 is minus 2. So that should be equal to 0. So X minus 2 is equal to 0. X is equal to plus 2. So the oxidation number of Fe in FeO is plus 2. Now in page number 160, you have the book back exercise, isn't it? Now in that third Roman number is your answer in detail. In that fifth question, you have three questions regarding the oxidation number, that is calculation of oxidation number. Let's see them. In the fifth question, the first one, A, carbon in carbon dioxide. That is, we have to calculate the oxidation number of carbon in carbon dioxide. We know the oxidation number of oxygen is -2, isn't it? Now, how many carbons are there? 1. So, 1 into x is 1. How many oxygen? 2. So, 2 into -2 is equal to 0. I always said that it should be equal to 0, isn't it? So, x, so this becomes -4. So, x minus 4 is equal to 0. X is equal to +4. So, the oxidation number of carbon in carbon dioxide is +4. Now, we'll move to the next sum, that is B. Manganese in MnSO4. So oxidation number of sulfur is +6. Oxidation number of oxygen is -2. So this will not be given in the question. You have to memorize this, right? Now how many manganese are there? 1. So 1 into x is 1. How many sulfur? 1. So 1 into 6. How many oxygens are there? 4. So 4 into -2 is equal to 0. So this becomes x. This is 6. And this is -8. When you subtract +6 minus 8, it becomes -2. So x minus 2 is equal to 0. So x is equal to +2. So oxidation number of Mn in MnO4 is +2. Next is the calculate the oxidation number of nitrogen in nitric acid, that is HNO3. Oxidation number of hydrogen is +1. Oxidation number of oxygen is -2. Now how many hydrogens are there? Only 1. So 1 into +1 plus how many nitrogen? 1. So 1 into x plus how many oxygen? 3. So 3 into -2 is equal to 0. So this becomes 1. This is x and this is -6. So when you subtract 1 minus 6, it becomes -5. So x minus 5 is equal to 0. X is equal to 5. So the oxidation number of nitrogen in nitric acid is +5. So with this we come to the end of the lesson, children. So your homework for today is that you have to copy all the numerical problems that I have done in this session in your classwork, and you have to learn these numerical problems, because numerical problems will be the compulsory question in your question paper. Now see you in the next class, children. Thank you.